Good morning, everyone. With pleasure, I'm presenting some of my research today with the title GPTune, Non-smooth and Mixed Variable in Surrogate Models. To start with, let me introduce you to our GPTune project. The GPTune project focusing on the problem of black box function optimization using Gaussian process. Here is our website. Our project provides a full software pipeline including a lot of state-of-art and modern features like history database support, transfer learning, sensitivity analysis, and multi-fidelity optimization. This is a joint project between the lab and Berkeley. So let's start with the basic problem, the black box function optimization. Suppose that you got a function whose analytic expression you don't know, but you can draw input response pair. Like if you assign location x, you can evaluate the function at the location x and get a response from it. However, such an evaluation is usually expensive. For example, imagine that you're doing the matrix multiplication, and then the maximal computational speed will obviously depend on the blocking strategy, more precisely the block size. If you actually plot the maximal computational speed here against block size, you can see there's a lot of zigzagging behavior, and there are two obvious drops near 116 and 500. We want to find the actual maximum here at 112. However, in practice, it's impossible that we actually exhaustively list all the possible block size from 1 to 1000. Therefore, we draw sequential samples, and then based on the sequential samples, hopefully we are building a Gaussian process. And then if the Gaussian process serving as a surrogate model is approximating the underlying black box function well enough, then hopefully we can learn this maximum point from the surrogate model. However, although Gaussian process is very widely used in black box function optimization, it also introduced some problems. For example, like the Gaussian process is so smooth. Like if we look at the right hand side here, the red dashed line here indicated the true function, and it obviously got a non-smooth point near x equals to 0. This sudden drops actually fails the Gaussian process, because the Gaussian process indicated by the blue solid line here is providing you an over-smooth mean function. The problem of getting such an over-smooth fit is that, well, you can see that the minimum obtained by Gaussian process here is quite a bit away from the true minimum, which is at x equal to 0. Observing this, we're trying to solve this problem. So the basic observation we had is that, again, with the same function, we will partite the domain into two partition components, that is -1 to 0 and 0 to 1 in this case, and then fit independent Gaussian process to each of this partition component. Here, the new fit will actually gives us much more accurate representation of the behavior of the black box function. And thanks to this accurate representation, we can actually hunt the minimum of the black box function better. So the main difficulty is that, okay, in practice, based on sequential samples, how are you going to find such an accurate partition? And to solve this problem, we propose this very normal cluster Gaussian process model. So we use a dynamic partition scheme. First, we use both the x and y to do a clustering. Then we got a set of cluster labels for which we fit into the classify algorithm. The train classifier will have a classifying boundary, which helps us to divide the whole domain into a more informative regime. On each of these partition components, we fit independent Gaussian process surrogate models. So the overall model is an additive Gaussian process. By doing so, we actually model the non-smoothness and also the partition regimes pretty well. And thanks to this additive structure, each of this Gaussian process can be fit individually and also parallelly. So not only we gain this non-smoothness modeling, but also we get a very good computational speed up. So here, let's look at an example, the famous booking number 6 function. In this function, its minimum is hidden in the valid, which is surrounded by a lot of wiggly parts of the booking function. So you can see here that our CGP model actually identifies this regime pretty well with only roughly 180 or 90 samples. And then it's beating the simple GP surrogates in over 90% of the times. By identifying the correctly partitioned regimes, we can see that the CGP with a lot of different exploration rates and other parameters is beating simple GP over 90% of the times, or as good as. Even if we replace the simple GP with a non-stationary kernel, roughly 70% of the times, 60 to 70% of the times, our surrogate model is faster for sure, and then is also outperforming the GP with non-stationary kernels. There's obviously a lot of these model parameters like exploration rate and also the sequential sample size of the optimization will affect the performance. But from this quantitative and qualitative results, we can see that the outperformance of CGP model is pretty consistent, and our approach is usually as good as or better than the GP with stationary kernel. Besides, our CGP model also gives you an innovative way of introducing the non-stationarity into the model when the context is an online context. It's completely different from the recursive partitioning like the tree model or random forest. So after solving the problem of non-smoothness, let's move on to a brand new problem, which is the black box functions with mixed variables. So again, we start with identifying the problem with Gaussian process. That is, the Gaussian process is usually defined for continuous variables only. Surrogate model should be able to approximate the function with mixed variable as well. For example, the continuous variable could be numerical variables like human's height, while the integer variables could be modeled after integers like human's age. And then the categorical variables, however, is much more difficult, like human's gender. There's no order and there's no magnitude information in the encoding. So it's much harder to actually incorporate this type of variable into any of the existing surrogate models. However, different types of variable really occurs in real-world application. For example, the hyperparameter optimization of neural network, among other machine learning algorithms. So our approach is to introduce this innovative new model architecture by combining the Monte Carlo tree search and the Gaussian process when we are building our surrogate model for the underlying black box algorithm. So more precisely, in our hybrid model, the Monte Carlo tree search will actually handle the categorical part of the variable, and the Gaussian process will still handle the continuous variable as we introduced earlier. So this architecture has at least two advantages. First, it unifies several past models that are proposed to facilitate the search approach among the categorical space. And secondly, it's very storage efficient because the Monte Carlo tree search only branches out at those combinations that you actually search. So it can handle much larger categorical space compared to traditional methods. And the dependence is described by Monte Carlo tree and the Gaussian process, as we detail in our paper. So as you can imagine, there's a lot of kernels already developed in previous literature to handle the categorical variable. But first, all of them, or most of them, were stationary kernel for the categorical part. We introduced a family of non-stationary kernel to handle potential non-stationary behavior of the categorical part. But a more imminent problem is that how we actually select from these kernels. Instead of selecting kernels at the beginning of the modeling, which is more like an offline context, we introduce this dynamic model selection scheme. That is, each time we observe a sequential samples, we select kernel. So this is much more different than the kernel selection problem in a fixed data set context, which we detail in our papers. The takeaway is that we introduced this new mechanism of dynamic model selection in the sequential sampling steps, and this will push the performance of our surrogate model into the next level. Again, we designed the kernel selection in such a way that the algorithm can be parallelized, so there is no loss of computational speed in our proposed hybrid model. So let's also look at this benchmarking. So in this benchmarking, we compare our hybrid model, which is on the top, which means it's the best, compared it against several state-of-art optimization algorithm that claim to handle the categorical variables. Here we repeat the same experiment with different random seeds for 20 times, and then let the algorithm run for 100 samples. So our hybrid model converges actually pretty quickly, and then reaches the optimum for the benchmark function, which is the modified Friedman function with 8 category variables. And then we can also see that our hybrid model also behaves as good as multiple state-of-art methods on real-world applications for the neural network hyperparameter optimizations, which we do not show here. So you can see that our method, which is on the top, actually converges to the actual maximum, which is 30, the fastest. And then it actually beats a lot of state-of-art methods. So let's also look at the box plot of the final maximums obtained by each of the surrogate model methods. Here is our hybrid model. So this box plot actually shows that our hybrid model systematically outperforms the rest models, probably, well, with one outliers. And then thanks to the fact that the Monte Carlo tree search is storage efficient, we are able to explore the categorical space more efficiently, well, in terms of storage. That means we don't have actually create a very large grid, but only like create such a tree that is very portable, and you can load it into your later models later. So to sum up, today we are introducing, well, 2 subproblems that we encounter in our GPTune project. One is the Gaussian process and non-smoothness problem. The main problem is how to model additive Gaussian surrogate models in an online context in order to solve the potential non-smooth behavior in the black box function. To this end, our solution is that an additive Gaussian process surrogate is proposed, namely the CGP, and the dynamic partitioning is automatically done in each step of iteration. The second problem we're treating is the Gaussian process with mixed types of variables. The main problem is that how to extend GP surrogate to search and model mixed variable space in an online context, when that means you can draw sequential samples from the black box function and model it. Our solution is to propose such a hybrid model with the Monte Carlo tree search part and the Gaussian process part. We also introduced the Gaussian process with kernel selection in order to address the non-stationarity as well as multiple kinds of kernels available in the online context as well. The advantage is that we got such a very storage efficient model, and also we got a best performance compared to some of the state-art methods. So I'll end up my talk here. Thank you for your attention, and questions are welcome. Thank you.